Okay, so we can start now. Let me share my screen first. So is it visible?
Yes.
Then of my video. Yes. Okay, so today we'll also first discuss some assignment question, week two assignment. Um, then we'll discuss our questions. Okay. This I saw this week two assignment question are much more easier, I think. Do you have tried this question?
Yes.
Okay, so should I do this question? No, or I can skip also. If you want, I can solve because I saw the solution, but in solution, actually the just answer is given. No solution has been provided. So then,
Okay, no need.
okay. Okay, then if you have any doubt in any particular question, you can ask me to solve that. Okay. If you feel that there
Okay.
is any doubt. Or one thing I can do, I will look at the question. If I find out any important question or any question which should be discussed, that question I will discuss. Okay. Otherwise, I saw most of the question are very basic question that can be solved easily. Okay.
Okay.
Okay. Then in this week we can start directly.
I have excuse.
Yes.
Please
Yes.
excuse. I have got one question to ask. That is
Yes.
for carbon monoxide.
Yes.
Question number 8. The value
Yes.
of entropy in joule per Kelvin per mole at T equal to 0 is. In that particular question, only the that is 1, 2, 3, 4, 5, 6 such type of options are only given rather than this 5.7 or 5.8. So that's why I clicked 6, which is an incorrect answer, of course, and
So
it was not
you are
been.
talking about the question for which week?
It is for the third week I am asking.
Third week. Okay. Okay. I didn't saw the third week question. Let me check on
Okay.
one. Third week question, right? Question number 8, you said. Okay.
Yeah.
Okay. And now repeat what you have said.
Okay, actually, when I was about to put my option, the only option it was showing it was either -1, -2, 0, 1, 2, 3, 4, something like that. So I opted for 6, but the correct answer was 5.7 or 5.8. So
Okay, but this is a
that option was not available.
I understand, but this is a fill in the blanks type of question, right? So,
Yeah, yeah,
but
yeah,
numerical answer type, NAT type question. So you have to
yeah,
write
yeah.
down the answer. That may be a fault of device. I don't know because I think. Okay, let me try to give answer. Is it possible to give answer? No, it's not possible right now. But uh, I think you should write down the value. While writing the value, you can write the fraction as well. 5.7, 5.8. Don't
Yeah,
know
that
because
can be written, but the thing is that such type of option was not being available. I saw that only some up arrow and down arrows are there, and in which only
okay,
1, 2, 3, 4 or
okay,
something
I understand.
that
Okay,
can be taken.
okay. Then that may be a fault of the
Some
setup.
system failure, yeah, some system, yeah, system
That does not
failure.
matter because you have to just check whether your calculation is right or wrong. Probably
Yeah,
because no number is given, right? No marks is provided due to in this assignment, as per I know. Is this there is marks
yeah, yeah, there is a marks.
that will be
I
added?
mine is wrong. Uh, Best
That
of
marks.
I do think will be
What
taken.
is
Na?
the
Best
course
of eight
structure?
will be taken.
These assignment marks will be added.
I need to see. But my in my previous FDB course, it was added.
You can see, I think, as you are saying, na, there is a problem. That's why probably 1 point, here is no point is mentioned. You can see in each question there is 1 point, 1 point. Probably they have also looked later that there is some technical fault. That's why they
No
probably,
point is
yes.
1.1 now. No
So,
point is there.
yes, because no point is mentioned there. You can see in each question there is 1 point, 1 point, but that 1 point is removed from this question. So probably they have also find out later something is wrong. That may
Maybe.
be. Yes. Okay, that is not that much important. That is just technical fault.
Okay, okay, fine.
Okay, so today we can now start. Okay. Mm, okay, first question will be right. Okay, first I um, plan to discuss uh, something in more details about the ensemble. Okay, so discuss the various type of ensemble. Because I saw the lecture, but I feel that there are some more discussion is needed regarding this ensemble. That's why I thought before discussing numerical problems, I should discuss this theoretical part because this is very, very crucial for statistical thermodynamics, this ensemble. Everything is based on this ensemble. So you have to first understand the ensemble. Um, actually, when I studied this thermodynamics, statistical thermodynamics, our coursework is started with the ensemble. After that, this molecular partition function, these things were discussed. But in this course structure, I found the first molecular partition function has been discussed, then this ensemble appears. But that is not problem. That's okay. But this ensemble is very crucial to understand. Okay. So first, okay. First, you have to understand what does ensemble means. The literal meaning of ensemble is, the collection or copy, collection or copy, you can say. This is the literal meaning of ensemble. Okay, now let's say uh, if you have any doubt, you will feel any doubt, you can ask me anytime. Okay, because this is very, very important to understand ensemble part. I will try my best to convey my feeling about this. Okay, first let's say there is a one mole or anything, some gas is there. Okay, this is a container. In this container, any gas you have taken. Okay. So this is the container of gas. So this container of gas, if you remember, we know that if it is real gas, there is a equation, right? PV equals to nRT. Okay. So what does it mean? PV equals to nRT. You remember this equation, PV equals to nRT. Okay. I think this is very basic equation. But now, what does it mean? That this state of this gas, ideal gas, let's say for ideal gas, can be the state of ideal gas is actually function of pressure, volume, temperature, and mole. If you taking 1 mole of gas, then it is P equal to RT. Means there are only three variables: pressure, volume, and temperature. So if you know the pressure, volume of or temperature, you can have the all details, all information about that gas. Okay, but so these are called independent variable. In independent variable. Okay, variables. But actually, how many these are variables? There are three variables: N, V, and T. Because you know R is a constant. R is universal gas constant. That is not variable. We are considering 1 mole of gas. That's why N is not written here. Otherwise, there will be N also. Okay, for 1 mole of gas, this is PV equal to RT. But now there are three variables. But how many independent variables are there? So there are two independent variables two variables because actually there are three variables, but they are related. These three variables are related with this equation. So how you can find out the independent variable? Independent variable is actually total number of variable minus number of equation. This is the number of independent variable, or you can say this is as degree of freedom as well. This is the formula. Or you can understand that why is the because let's say if you know P and V among these three, P and V, you can easily find out the value of temperature using that equation. So if you fix P and V as independent variable, then T will not be an independent variable. The value of T will be fixed. Okay. Let's say if you have the value P equal to 1, V equal to 1, then obviously the value of T will be 1 by R. You can't change this. So that's why T will not even as now an independent variable. P and V are independent variable now, but T will not. Similarly, you can fix PV, or you can fix PT, or you can fix VT. Any two independent variable you can choose. So these three are actually the parameters of a system. This is a classical macroscopic system. You have to understand this. You have taken a container which is filled with a gas, filled with the gas, classical gas. That may be ideal or not. That is not important, because let's say if it is not real gas also, if it is not ideal gas, if it is a real gas, then you don't know the relation between P, V, and T. But you know that thing that there must be a equation that might not be that is not known right now. Probably you can approximate even, but PVT are related. Always PVT will be related. If you take any real gas in a container, PVT will be related. That means you will always have two independent variable, and another variable will not be independent anymore. Okay, so state, this state of the gas is called macro state. Very, very important. This is called, let me write, this is macro state. Why macro? Because you can see it. This is a classical thing. You can see the container of the gas. So this container of the gas is, is a macro state. How the macro state is defined? Defined by these variables, P, V, and T. You can define by other variable as well. You can define by NVT. You can define NVE. Anything. You can define by anything, but any parameters, but that should be that should signify a macro state. Okay, so a macro state means a classical state, classical thing. You can see that, you can feel that. So this is a container of a gas. Now under this macro state, okay, let's say under this container of a gas, for a particular time, if you take a picture, a snapshot, for a particular time, the position of the molecules will be will have some pattern. After next second, after 1 second, the pattern will be changed, right? So what does I mean? What I want to mean that, let's say, hmm, let's say this is the pattern, or this is the distribution of molecule, not pattern. Distribution is the right word. After a particular second, the pattern distribution will be changed. Same distribution will not be there because the all gas molecules are moving, right? So that's why these are always changing. So now let's say anybody want to calculate a property of this system. What are the property? These are variable. These are not the properties of the system. What are the properties of the system? Properties of the system are properties of a properties. Properties are, you can calculate the internal energy. These are thermodynamic properties. Internal energy, that is U or E, whichever you can write. That may be enthalpy. Okay, that may be entropy. Anything, that can be Gibbs free energy. That can be Helmholtz free energy. These thermodynamic properties you already know. Okay, these properties, if you want to calculate, let's say now how you can calculate these properties. That is our that was our goal, now. Because in classical thermodynamics, we always deal with this macro state. We don't look at the interior of the macro state, how the molecules are distributed, how the particles are interacting. These things we don't consider. That's why there is a term that thermodynamics or classical thermodynamics is very much universal. Means that does not depend which type of gas you are taking, which type of gas you are considering. In classical thermodynamics, when you are considering a gas, container of gas, that may be a carbon monoxide, that may be oxygen, that may be helium, that may be anything. So in detailed description means the description in molecular level is not important in classical thermodynamics. That's why in classical thermodynamics, you can't calculate the absolute value of these properties, this internal energy, enthalpy, or entropy. For that, you have to consider the statistical picture. That means the orientation, distribution, this you have to consider. Otherwise, you can't calculate because there are infinite number of molecules. So you have to account that distribution. You can't ignore that. So now, if anybody want to calculate, let's say the any property among these, I am writing by X, any property X, you have to calculate. So how you can calculate this property? Okay, these properties are characteristic properties. So you have to calculate this X. Okay, but what we have discussed, that this microscopic picture, this is a macro state, but under a macro state, the microscopic picture means the distribution of the molecules is always changing. So microscopic picture, let me write it. The microscopic picture, microscopic picture of the system of the macro state or macroscopic system is always changing, right? Changing with time. Okay. So if the microscopic picture is always changing with time, so now if you want to calculate any property, let's say you have to calculate that property X. That may be E, U, H, anything, S, G, any property that may be, I'm writing by X. Now, if you want to calculate the X, then how you can calculate? If is this clear? The microscopic picture and the macroscopic thing. Uh, let's say I should explain more. Let's say this is the macroscopic picture. Okay, macroscopic macro state. Let's say there are four energy level. Suppose there are four energy level, and two particles are there. Two particles are there, A and B. Now this may be a microstate, microscopic picture of under this macrostate. After a time, after 1 second, let's say next, what it can be, let me draw it. Okay, in after a few seconds, maybe this picture will be changing. Macrostate will not change. Macrostate is remain same because macrostate still contain four energy level, two particle. So, but the distribution, oriented, this distribution changes. It may be AB here. It may be let's say AB here. Anything may happen. This is always changing. If as time passes away, this distribution will always change. So that's why the macro state is remain same. You have to understand macro state remains same with time, but the microscopic picture of that macro state under that macro state is always changing with time. This macroscopic picture, which we have already discussed in our previous um, discussion, that these macroscopic pictures are called orientation, distribution. We have termed this, right? But these are called actually the micro state because this is actually the microscopic picture. So these are termed as microstate. These are all microstate. Okay. So what we understand that under a macro state, microstate is there. Macrostate remains same, but as time changes, microstates are changing. This is called folder file relation. As you know, na, in a folder, in a computer, there are lots of files. So like this. So under a macrostate, there are lots of microstate. Is it clear? So a macrostate, here we can see there are many more microstate will be there. So there is a, let me write it. In macrostate and microstate, there will be a folder file relation. Okay. So now, if this is clear, then it is easy to understand that now, if you consider the x, that value, that x you have to calculate now. How you can calculate? Because for this microstate x is different, for this microstate x is different, x will be changing. Instead of x you can consider the internal energy that will be changing, or entropy always changing because the distribution is changing. So obviously to calculate x you have to calculate the average value of x because this is changing. So how you can calculate this average? This average should be the time average of x. Now you can understand because why time average? Because the x is why x is changing because time is changing. Let's say if you want to calculate the population of India for last 100 years, how you can calculate the population which is changing with respect to time? Then you divide it with 100. That will be the average population, right? How you can calculate this? So this is called the time average property. So here also you have to calculate the time average of that property. Okay, this is the average of that property. Average of any property x. So how that this time average is calculated? It's easy. How this x is varying with time. So x is a function of time t dt, and time is varying from 0 to, let's say, any finite time tau. You have to divide it by 2. You can think like a population. It's easy. Let's say you have to calculate the population for last 10 years. How you can calculate? You have to calculate population from 2010 to 2020. So you have to calculate the population for first 2010 plus 2011 plus 2012 and up to 2020. Then you have to divide it by 10. That will be the average population. That will be average population. Okay. So what does it mean? What you have done? You have taken the population which is a function of time and you have taken the total population. This is a here we have taken summation, but if it is a continuous thing, then you should consider integration. And then you have taken the total time tau. So it varies from 2010 to 2020. So you have to take here 10 years because it is total span is 10. So here you can see that we have written the same formula. X, which is a function of t, so xt into dt, which is varying from 0 to tau. This is the time span. You can consider this from as t to t plus tau. That does not mean. That is same. So 0 to tau, what is the time span? Tau minus 0. How it is 10? It is 2020 minus 2010. That means 10 years. So here also the time span is tau minus 0. So it is 1 by tau. So in this way, you can calculate the time average. This is the formula for calculating time average. So this thing you can box it. This is how. Okay. This is the thing. Okay. This is the time average. So you have to calculate this time average. But what happens? This time average is not possible to calculate. How you can calculate? You know this xt. This is also changing with time. This is not possible to calculate this time average. So that's why we have to bypass this problem. We have to here the ensemble will arise. So this time average is not possible to calculate. Time average is not possible to calculate because you don't know this xt for a particular time. You can, let's say, you can calculate, but this time is continuously changing. Time is a continuous thing. So how you can calculate x for each and every time between 0 and tau? So this is not possible. So that's why time average, calculating of time average was not possible. So then Gibbs give an idea, gave an idea that instead of time average, it's better to calculate the ensemble average. That we studied, this ensemble average. What does it mean? Let's say, as you have discussed here, what we have discussed, this is changing, right? The microscopic picture is changing each and every time. That's why we had to calculate the time average, because that microscopic picture is a function of time. In, in ensemble, Gibbs says that, what Gibbs says? No. Gibbs says that, okay, time is not changing. Fix a time. T is fixed. Time is fixed now. But at a particular time, you make a infinite number of copies. You make a infinite number of copies at a particular time of that macrostate. Means that you had that macrostate, this macrostate, you made the infinite number of copies of that macrostate. Xerox copies you can consider. These are the infinite number of copies. So then what will happen if you consider the infinite number of copies? That infinite number of copies, collection of that infinite number of copies is called ensemble. Ensemble means the collection. What does it mean? That now when you make the infinite number of copies, obviously all arrangement will be included. All probable arrangement, let's say A is here, B is here, A is here, B is here, AB here, AB here, AB here. Every arrangement will be included when you are considering the this infinite number of copies. Here I have drawn only 8, but you have considered the infinite number of copies. So every arrangements are there. So when P is varying and the microscopic picture will changing, that for that the copies will be generated. This all microstate will be generated. That all microstate will be accounted by using this ensemble. That is the picture. That is the beauty of this consideration, because you have to consider the all microstate, all microscopic state under a macrostate to calculate the average. That may be generated by changing the temperature, or that may be created by considering the infinite number of copies. So that is the difference between time average and ensemble average. So now you can calculate the average. How? How you can calculate the ensemble average? Because now time is not changing. As per time is not changing, it is easier to calculate. This is the ensemble average. How you can calculate the ensemble average? You know that, let's say this is the xj, pj, and sum over j. Xj is the uh, pj is the probability of the jth state, because under this infinite number of copies there will be so many states, and xj is the that particular property for that jth state. By using this, you can calculate. This is the average ensemble average formula. So this is our ensemble average. And what was our um, time average? Time average formula was 1 by tau 0 to tau xt dt. So these are comparable. This was proposed by Gibbs. These are comparable when there is an infinite number of copies. Infinite number of copies. So now we can calculate this ensemble average. Okay. Probably this is clear. So instead of using time average, we should consider the ensemble average.
May I ask some question?
Yes.
Could you please explain PJ in detail?
Yes, I will explain. Okay. When because this PJ will changes for different type of ensemble. So that for that we have to consider a particular ensemble. Then we will discuss the PJ. PJX, all thing I will discuss. Okay. So in this context, I must say one thing, one definition that I have said verbally, but there is a particular words. Huh. Okay. Let me write it. Okay. Time average of some property of a macroscopic system at equilibrium, because these all are equilibrium, we are not considering non-equilibrium, is comparable with the instantaneous ensemble average. Okay. This definition was given by Gibbs. Okay. And this hypothesis is called ergodic hypothesis. Let me write it. This is called ergodic hypothesis. Okay. That this is same thing. This is the mathematical form, and I have just written down in statement. The time average of some property of a macroscopic system at equilibrium is comparable with the instantaneous average. Why instantaneous? Because if the time is fixed. For ensemble average, we are not changing time. That's why it is instantaneous ensemble average. But when this ergodic hypothesis will valid, this is not valid always. I have also said this. So when this ergodic hypothesis will valid, first is the system. Let me write it. The system, the macroscopic system, should consist large number of molecules. Okay, large number of molecules. Then only both picture will be equivalent, so that we can randomize uh, both averages. Okay, you can randomize the picture. And second thing is that the number of system in ensemble, the copies, number of copies, the number of copies of the system in ensemble should be very, very large. That I have already mentioned, the infinite number of copy you have to consider. Then it will replicate the all microstate which will be generated by changing with the time. You have to feel this. You have a macro state that will be when time is changing, the microscopic picture of that macro state will be changing. That should be generated. The all copies should be generated by considering the average. Let me again explain it. Let you consider in a room you are only one person. You are staying in the room. Okay. Now from day to night, from 6 p.m. to let's say from for in a particular day in 24 hour, your position will be changing in the room. You are not escaping from room for a second. Let's consider. Okay. Then your position will be changing. Sometimes you are in the bed, you are in the floor, you are walking, you are sleeping, everything you are doing. So that means your position, if you consider your position, that is changing with time. For a particular time, there is a position. After a certain time, the position may change. So now, if anybody want to calculate the average position, how we can calculate? He has to consider the position x, all position x, and all that your coordinate q position that will be obviously x, y, and z function of x, y, and z, and time. These all are changing. Then you have to make it dt and you have to integrate it for all day for 24 hours. Then you have to divide it by 24 hours. Then you will have the average position, right? This is the definition for taking time average. So what does it mean that for each and every time one picture will is generating, right? Let's say for 6 p.m. there 6 a.m. there is a picture. 6 1 after 1 minute there is picture after 1 second even. For each and every second one picture will be generated. So how many picture will be generated? This number of into 24, this number of pictures will be generated. Then you have to take the average. That will be time average. Correct. So what the ensemble average is saying, now you are not taking, you are not changing time. At a particular time, at a particular time, you have to set that you have to create infinite number of pictures. Okay. So now, let's say for a particular time, when you create infinite number of 10,000, let's say 10,000 picture or 1 crore picture you have created at a particular time. So under that 1 crore picture, all position are included. So these all pictures which are generated due to changing time will be included under this 1 crore picture, should be included. That is, this is the ensemble average and this is the time average. These picture are generated by changing time, and this picture is an instantaneous picture, but at a particular time all probable condition are accounted. So that is the ensemble average. So it's clear that this number should be huge, then only this all number can be replicated. If it is only 1,000, it's not possible. You can't say both are same. But when it is, let's say 1 crore or 10 crore, it can be said that both averages will be same. So I think probably it is clear now. You can think it more. So that's why there is nothing wrong in considering the ensemble average. This is a excellent thinking. That's why he gives this great. Okay. So now you can do this. Okay. What was our question now? That you have to discuss the various type of ensembles. Then we'll discuss what you have asked. So how many ensembles are there? How many ensembles are there? Obviously, that depends on the macro state, which macro state you are taking, because you are making the copies of macro state, infinite number of copies. So eventually, the type of ensemble will depends on the macro state. One thing you have to keep in mind that in ensemble there are infinite number of copies, but for each copies the macro state is same. Macro state is not changing. Micro under a particular macro state, the microscopic picture is changing. That means micro states are changing. So this is a copies of, so ensemble is a copy, this is a infinite number of copies of a particular macroscopic state. Macroscopic state is not changing. So obviously now the type of ensemble will depends on the which type of macro state you are considering. So let me discuss this. This is also very important. From here, so many questions are formed. So ensembles. So there are mainly three type of ensembles are there. Other ensembles are also possible, but majorly three type of ensembles are there. First one is micro-canonical ensemble. Micro-canonical ensemble. Let's see, like micro-canonical. Second one is canonical, and third one is grand canonical. So second one is canonical ensemble, and third one is grand canonical. This was discussed in class. Ensemble. There are three ensemble. Okay, we'll discuss these three ensemble in detail. Uh, so first, micro-canonical ensemble. Okay, so under micro-canonical ensemble, that macroscopic state, this macroscopic state you are considering, this macroscopic state, you have to make the infinite number of copies of this macroscopic state, right? Infinite number of copies. So let's say like this. Though it should be infinite, but here it's not possible to draw infinite number of copies. It's looking back. Like this. These are all copies of this macro state. Now, under microcanonical ensemble, these all copies are, this is a microstate. Under this macrostate, these are infinite number of copies. So these are all different microstate, all different microscopic pictures. So these are all microstate, right? This is a macrostate, this is a all microstate under this macrostate. So I am repeating this again and again because this create huge confusion. If you don't understand this, later you will not understand the relation between the ensemble partition function and the molecular partition function. So these are all different number. This is actually not 25. Here it is 25, but this is actually infinite number of copies. So while making these copies, if these systems are, each copies are, each copies are, or each microstates are, these are all microstates. So all microstates are isolated. Means they are not interacting. This microstate is not interacting with this microstate. This interaction is not there. So these microstates are not interacting. These are isolated. So you know the isolated meaning. What does mean? It mean in thermodynamics that no energy is transferred and no particle is transferred between any two system. If one system is isolated with the surrounding, that means system is not interacting. Okay, you can understand this microstate. This macrostate is also isolated. This is not interacting with the surrounding. That means no energy is exchanged, no particle is exchanged. So how you can define this macrostate? How you can define this macrostate? By N, V, E. These three are constant. Number of particle are constant because that is not changing. Volume is constant. Volume should be always constant because you're making copies of that macro state. So you're not changing the volume here. So volume is constant and energy is also constant. Everything are constant. So NVE is are the constant parameter for a macro state under microcanonical ensemble. And now you are making infinite number of copies of that macro state. So for each and every copy, this NVE is same. This is not changing. This NVE is the same for in all copies. This is microcanonical. Next is canonical. So how you can one thing I missed. This should be said. That means these walls between two states, these walls are rigid. That means these walls are rigid. Rigid means that is not allowing the microstates to exchange energy or particle. That's why these are called rigid walls. And all system remains isolated. Okay. So how you can signify the microcanonical ensemble by N, D, E. Next is canonical. Canonical is in canonical ensemble. Okay. So under canonical ensemble, how the copies will be there? Let me copy it. I but NP is equal. Okay. Let me write it. So again, these are all copies. Okay. Now here, these are all microstate under a particular macrostate. This is the macrostate. And these are all infinite number of copies of this macrostate. Here, this macrostate is actually interacting with the surrounding by exchanging the energy. Energy is being exchanged. So that means here all microstates are interacting by exchanging the energy. Then only the energy will be changed. Otherwise, how you can change the energy? So here the energy is not fixed for each microstate. This energy is changing. This energy is changing. How energy can change? That means these walls are not rigid anymore. These walls are not rigid anymore. These walls are, let me change the color. These walls are not rigid. These walls are heat conducting. Then only the heat will be exchanged. Here the energy is exchanged. Energy means heat. Heat is exchanged between the microstates. So here in all microstates, the heat is exchanged. Okay. So now how we can define, similarly, how we can define the canonical ensemble? N is constant because particle is not exchanged, so N is constant. V is constant. But now E is not constant because energy is changing. For each microstate, the energy is not same. So E is not changing. But in what we consider that here, this all this collection, infinite number of collection is actually is in a thermal bath. That is a thermal bath. This is also said in the class. This is in a thermal bath. Therm means the temperature is constant. For this infinite number of copies, the temperature will not change. Energy can be exchanged, but ultimately the temperature should not be changed. That means E is constant for the macrostate. T is same. Okay, so temperature is same, but the energy can be exchanged. Okay, it's going. Oh. So NVT, I think it's clear. So canonical ensemble is actually defined by NVT. NVT. Okay, so this is great. Okay, so here the system are, let me write it again. Here the system was all microstate were isolated. Here all each micro states are not isolated, they are closed. In thermodynamics, you know that closed system means only energy exchange is allowed. Energy exchange is allowed, number of particle exchange is not allowed. So then obviously this picture will be generated. So this is the canonical ensemble. Generally we will study the canonical ensemble because this is more relevant. The number of energy is fixed, temperature is fixed. In our practical situation, classical situation, this is more common case, canonical ensemble. That's why always the canonical ensemble is discussed. And one more thing, that is the grand canonical. Okay, that should be discussed also in similar way. Grand canonical ensemble. Okay, grand canonical ensemble. Here, let me copy it. Is it possible? Yes. Otherwise, I have to draw all figure again. Hmm. Okay. So in case of grand canonical ensemble, these are the copies, and in this is the macro state. Here, the macro state is also interacting with the surrounding, and here both energy and particle both are exchanged. Energy is also exchanged, particle is also exchanged. So here microstate, in between the microstate, E is also exchanged, N is also exchanged. Both energy particle both are exchanged. That means this wall is not rigid. Wall is not here. Wall was heat conducting. Here, here the wall will be. Here the walls are as well as heat conducting and also permeable. Okay, both because particles are also exchanged. Both are there. So this is the grand canonical ensemble here. So ultimately, that as the number of particle is not fixed here again. So what is fixed here? V is fixed. Temperature is fixed similarly because that there is a thermal bath, and here the number of particles are exchanged. So ultimately, after exchanging energy, the temperature becomes equal. You know from zeroth law of thermodynamics, if in two bodies are there, when energy is being exchanged, ultimately at equilibrium, temperature will same. That's why there is a thermal bath. You will be same. I think this is clear. Here also, when two species are there, when particle is being exchanged, until how long the particle will be exchanged between two bodies? Until the chemical potential is same. This is the definition of chemical potential. You know from classical thermodynamics. When the chemical potentials are same, then no particle exchange will be there. So ultimately, for all microstates, the chemical potential should be same. Number of particle is not same. Number of particle are different. After exchanging particle, the chemical potential will be same. So there will be mu Vt. Okay. So here not only thermal bath will be there, also thermal bath uh, maintaining chemical equilibrium. So this is our grand canonical ensemble. Okay. Anything remains? Yes. So here the write that each microstates are open open system. Open means that can exchange both, that can exchange energy, that can exchange number of particles. So here you can write that this is mu v t. So there are three ensembles. I think now it's clear. Also, one more ensembles are there. Just I mentioned this. One more ensemble you can generate, that is called isothermal ensemble. So from the name, you can understand what does it mean. Isobaric means pressure should be same. Temperature, isothermal means temperature should be same, and the number of particles same. So NPT will be same. This is the isobaric isothermal ensemble. So basically there are three type of ensemble: canonical, grand canonical, and microcanonical. Okay, so I think this is now clear. So I wanted to discuss this because this is very important uh, to understand the ensemble. Then you can follow the anything, the average values, everything. Okay.
May I ask one question?
Yes. Awesome.
Again, isobaric isothermal ensemble. I
Yes.
think we are talking about ensemble which has got a definite volume. I mean, the same volume ensemble have that you have stated earlier also. So,
No, no, no. In isobaric isothermal ensemble, the volume is changing.
volume is changing. Okay,
Volume
okay.
is changing.
So, does it contradict that ensemble concept?
No, no.
Because
Here you have that always depends on microstate, right? Macrostate. In thermodynamics, classical thermodynamics, always volume is not constant. Sometimes pressure is also constant, right? Let's say you are considering a chemical reaction. Under that chemical reaction, volume changes, but the pressure remains constant. That goes under 1 atm pressure. So you can think like that. Always, it's not necessary that the macro state is a gas content that is contained in a container. Not like that. You can think like that. Our reaction, that is also macro state. That macro state, under the macro state, the volume is changing, but the pressure is constant. The temperature is constant. So that may be there.
in the purview of ensemble theory, means we have got a replica
Hmm.
of same volume of all the
No, we have to make the copy. We have to make
yeah,
infinite number of copy of that macro state. Volume may be changed. Volume may be
okay,
changed. You have
okay.
to design the copies in that way. Then here in this, like this figure, you can't make that NVT ensemble. Sorry, isobaric isomer ensemble. For that, maybe ensemble may looks like something that copies are same, not same. Sometimes volume is this, sometimes volume are that.
Yeah, yeah, yeah.
In that
So,
way, you have to draw.
can you give some examples of this type of ensemble where it is being used?
Mm, Ultimately, what happens, this later you will see that all ensemble, you can take isobaric, isothermal, anything. Ultimately, all ensemble merges, gives the same result. Okay, so ultimately there is no need to consider a different ensemble. I don't know the your question, the answer, the particular example for isobaric isothermal ensemble where it is used, but later you will see that that grand canonical ensemble, that microcanonical ensemble, both are same with the canonical ensemble. Will merge, will merge. So that's why ultimately there is only one ensemble remains, canonical. That's why canonical is studied, because that is easier to
Okay,
understand, and ultimately that will make the same result. So why we should consider that? Okay.
okay, thank you.
I'll search for the particular application for ISO, because I know when the grand canonical ensemble is used, particularly canonical is used, but for isobaric isothermal ensemble, this particular example I don't need. We have to design such a physical system like that when pressure is constant and temperature is constant.
Okay, thank you.
Okay, now let us discuss some question. Okay, first question it is discussed. Okay. Question number 2. Calculate the heat capacities considering canonical ensemble. This was not calculated in class, that's why. The internal energy has been calculated. So now we will calculate the um, heat capacities. Okay. Yes. What is the partition function for canonical ensemble? That is defined by Q. That's why the Q is a function of N, V, T. You may give the commas. There should be comma. N, V, T. This is canonical ensemble partition function, which is defined as sum over J. Gj must be there if there is degeneracies, or then e to the power minus. If there is no degeneracies, then it will be only e to the power minus beta Ej. And this energy is also function of N, V, and P. So this is the canonical ensemble partition function. This is already discussed in class. So when you study the grand canonical, you will see the partition function for grand canonical. You can see the structure of the partition function is quite similar with our molecular partition function. The molecular partition function was like this, but this is not molecular partition function. This is canonical ensemble partition function. Here we are considering the infinite number of copies of that macro state. So how we'll relate this capital Q and small q, that will be discussed in next week probably. We have to consider now under each macro state. Uh, okay, one thing I should also mention, from where that molecular partition function arises. This is a macro state, right? We are making the infinite copies, but under this particular macro state, when you are considering for under this is a one copy of that macro state. Under this one copy, you have infinite number of molecules. So there will be molecular distribution as well. So that molecular distribution gives you the molecular partition function. Okay. So for each and every copy, you will have a Q. You will have a small q, molecular partition function. And from that small q, you have to consider the infinite number of copies of that ensemble to generate the capital Q. That will be discussed in next week. So I should not discuss here. Okay, Q is known. So how you calculate the internal energy? Okay, you asked me that Pj. Okay, let me also discuss that. What will be the average for any quantities? This is already discussed. Xj, Pj means, let's say there are so many energy levels are there. Okay, E1, E2, E3. You have to understand this. Okay, we are considering canonical ensemble. These energy levels are not molecular energy level, not vibrational, not rotational. These are not that energy levels. Okay, these are energy levels for that copy, this infinite number of copies. Because in this infinite number of copies, this energy are changing. For each microstate, energy is not same. Let's say there are some A1 number of copies for which the energy are E1. A2 number of copies for which energy are E2. That is that energy here. These energy levels are for that. These represent the number of copies, energy of the copies in the ensemble. Okay, so in that Pj means the occupation probability, fractional probability for that jth energy level. If Ej is there, that is the Pj, and Xj means that under that energy level, what is the value of that particular property, internal energy. If you are considering internal energy, then it will be Ej. So just you can write it for E. If you calculate the average energy for average energy, which is internal energy, then you have to write it just Ej Pj. probability of that PJ, finding that energy level PJ and the energy EJ. So, and you know, the derivation are similar, but the picture is different. Okay, what is the PJ? You know, this PJ should be e to the power minus beta EJ by Cartesian function Q. That, because the overall treatment is same. This is PJ. So you can write it as EJ beta EJ by Q. So this will be our average energy or internal energy, whatever you can write. So how you can calculate this? Then you know Q is sum over J e to the power minus beta EJ. So when you make differentiation, okay, one thing you have to always carry out, this EJ is function of NVT. So Q is also function of NVT. I have written earlier. Okay, I have written here NVT. So here I should write Q NVT. So when you differentiate with respect to, let's say, beta means temperature. Beta is all means 1 by kBT. So it essentially signifies the temperature. Okay. And the volume should be constant. N and V should be constant. Then because this is partial derivative. So it will be sum over J beta e to the power minus beta EJ. So what will it give? That minus EJ e to the power minus beta EJ in beta. Okay. So this numerator has arrived here. So what you can write it? So you can write that sum over J e to the power minus beta EJ is essentially minus uh, del Q del beta constant of NV. Okay. So sum over J EJ e to the power minus beta, let us divided by Q, then it will be just 1 by Q. So, and this is the internal energy. So minus Q del beta NV. The same formula we were obtaining our molecular partition function, but remember in molecular partition function there was no N, but N is there. Okay, so this is our internal energy. Now you have to calculate the heat capacities. How you can calculate the heat capacities? What is the definition of heat capacity? There are two type of heat capacities. Heat cities, SI or T, I don't know. Heat capacities. CV and CP. CV means del U, del TV, and CP means del U, del T, P. You have to calculate this. Okay. So U means you know. So CV, first you have to, we are calculating the CV. CV, so you can write it like this. Okay, so this is our CV. So that means del T. What is the average energy? This is the average energy. That is 1 by Q del Q del beta NV, and here also volume density. Okay, so this is our CV. Also, you can simplify this as well because here instead of beta, you can write it in terms of temperature as well. It will be kBT square del Q del T NV also, because beta is just kBT square. You can put there, or you can write it just d ln q del beta in v. That is also correct. You can write anything. All forms are equal. Okay, so now just t is there, right? So that's why I written, because t is there, so it is better to consider this formula, that kbt square del q del t at nv. So what will be that? Kbt square is constant, and so two terms will be there. Kb is constant, kb will be out, and del q del t. So t q is variable, q is a function of nvt, so that we can't make out. So it will be, first let's say kbt square is coming out, then it will be d2q dt square nv plus del q del t kb, and t square will be 2t, so it will be just 2 kb. So this will be our cv. Okay, now cp you can try in home, because cp there is pressure, so you have to consider that thermodynamic equation of state. You have to just, nothing is there, cv is there, so cp you can calculate, right? Because there is a equation cp minus cv, that is nr, while considering, when you are considering the ideal gas. But there is a in general equation for cp minus cv. If you consider that, you can calculate this. This is, nothing is there. Okay, so should I do this, or you can calculate the cp minus cp, you can calculate?
Please show us.
Okay, okay, so let me do, I think cv is correct. Let me check whether cv is correct or not. Is there any, 1 minute. Okay. Okay, this is correct. This is correct. LNQ del V. Okay, okay. So this is okay. LNQ. Okay, that's why I'm thinking. Okay. So let me show this first, because there may be some doubt. What we have obtained, that 1 by q del beta NV minus. This was our internal energy, right? So instead of q, you can write LNQ. If you write it d LNQ del beta, what does it mean? Just make, let's consider LNQ equals to Z, then it will be instead of ln q, if you put q here, then it will be dq del beta nv into dln q dq. And dln q dq, you know, uh, there will be 1 by q, that 1 by q is appearing from there. Okay, minus 1 by q. So it essentially means these are same. So I think there is no doubt. You can write it. You can write it. Hence, now beta is equals to minus sign will be there. Beta is equals to kbt. If this is true, then you can write it like minus dln q dt into dt del beta nv, obviously there. And del t del beta means t equals to 1 by kb beta. So del t del beta 1 by kb will be there, and it will be just del beta of 1 by beta. So that means 1 by temperature is 1 meter. Temperature is, it's correct. So it is kb. So del beta 1 by beta is minus 1 by beta square. So you can write it, minus minus will be plus, it will be dln q dt, and it will be 1 by kb beta square. Okay, now just put beta will be, beta is 1 by kbt, so it will be kb square t square. So essentially it means kb T square dlnq del T. So this form we taken kBt square dlnq del B should be there. So kBt square dlnq del T. Okay, so I think this is now clear. And here also we have to write the dlnq, not the q. I written wrong first, so that's why I checked. So it is first kBt square is there. It will be d2 dlnq del T square nv plus 2 kBt dlnq del T nv. Okay. Okay, now Cp. Okay, so Cp just for ideal gas. First, I'm doing for ideal gas because what was the general formula? Just do you remember the general formula for Cp minus Cv? Just you have to add that. Otherwise, everything is straightforward. First, okay, first for ideal gas, it is just Nr. You have to just add Nr, and then the rest of the part is clear. But how you can write Nr? You have to write the Nr. You know this. R means R is gas constant, right? Gas constant. How you can calculate the gas constant? NkB, right? So instead of Nr, you can write capital NkB, NAKB. This is clear. So instead of Nr, you can write NkB plus Cv, and Cv is already known. Cv is already known this value. Cv is already okay. That is already known. Okay, so this is for ideal gas. But for a general case, you can also do. I can remember right now the formula. There is a formula I have from which you can calculate the Cv minus Cv. So for using that, by using that formula, you can easily calculate that. I will do that in next class because currently I have to look at for the formula. I can't remember, but it is straightforward. It is for ideal gas. Okay. Lighting is getting okay. So it's okay. Now what we can, okay. Third question. Microstate, macrostate already we have discussed. This is important. This is also important. What do you mean by thermodynamic limit? This is very, very important question. Thermodynamic limit. We are talking about so many things, but first we have to understand what this should be discussed earlier. I forgot, but okay. What does it mean by thermodynamic limit? You are considering ensemble, right? So here, in case of let's say any macrostate you are considering any macrostate, this is a macrostate. So how many molecules are there? If there is only one mole of molecule, then also there is an infinite number of molecules because one mole is 10 to the power 23. You know, okay. So n, the number of molecules n is going to infinite. Volume is also infinite. Why? Volume is infinite because the volume with respect to that molecule, if this is the molecule, for that molecule, with respect to that molecule, the volume of the container is infinite, obviously infinite. So that's why what happened that n by v, this ratio become finite. Okay, this ratio become finite. That is called thermodynamic limit. That n by v ratio should be finite. In which limit? In which limit? Under this limit, the n by v ratio become finite. Under that limit, only this entire discussion are relevant. the statistical thermodynamics, everything, all discussion we are doing, yeah, everything will be relevant under this thermodynamic limit only. So there is a very interesting plot. If you plot N and V, here let's say N and V, or let's say like this, we can plot in box. In one direction there is N, another direction there is V. N and V we are plotting. When N and V are very small, sorry, not very small, both are infinite. In this region, both are infinite. So in under that region only, when both are infinite, N also infinite, V also infinite, then N by V is finite, and this is our classical thermodynamics or statistical thermodynamics. Because in classical thermodynamics we are considering the container, and in a container N is also infinite, V is also infinite. So this area essentially signifies our classical thermodynamics. Under this classical thermodynamics we are discussing the statistical picture, the statistical thermodynamics, but this picture is here. But now if you consider this area where the number of molecules also very less and also the volume is less, that means this n is sorry, this n is also tends to 0, v is tends to 0, means you, let's say, two atom are there only. We are considering a system where only two atoms are there or two spins are there, like this system, two pins are interacting. Under this considered system, both are tends to 0, but you see n by v will again finite. Both are approaching 0. That's why n by v will finite. So here also thermodynamic limit is valid. N by v should be finite. So this is called our quantum thermodynamics. But other two limits are very, very subtle. This limit and that. In this limit, you can see n is going to infinity, but v is not. V is going to 0. Here n is going to 0 and v is going to infinity. So under these two limits, the thermodynamic limit is not maintained. That's why these two limits are not allowed actually. So we have to deal in these two. Okay. I both classical and quantum thermodynamics. This is called the thermodynamic limit. Okay.
Can you please repeat this quantum thermodynamic n
Okay.
by v finite, how it is
Let's
becoming?
say n going to tends to 0. Okay. V is going to tends to 0 also. Or let's say for your convenience, two particles are there. Only two. Two particles are interacting. So n is 2 and volume will be also for one molecule. The volume is not 0. Volume is also comparable. What does I want to mean that this volume is for the system volume. That system volume and the number of particles, if both are tends to 0, then uh, n by v, what will be n by v? That is a ratio that will be finite now. If both tends to 0 or both tends to infinite, then ratio should be finite. Let's say 10 to the power 50 divided by 10 to the power 49. Both tends to infinite. Then the ratio will be 10. That is a finite quantity. Or let's say 10 to the power minus 50 divided by 10 to the power minus 49. Both are tends to 0, but the ratio is 0.1. That is also finite value. That's why I'm saying in both cases, thermodynamic limit is obeyed. That n by v is there. So that is called the thermodynamic limit. Okay.
Okay, there may be cases where the volume is infinite, but the number of particles may be very small.
This
Uh,
I said. In that case, thermodynamic limit is not obeyed. So that is not practical condition. Okay, that these two regions are not allowed. You see now when the number of particle is zero, tends to zero, that means very few particles are there and the system is huge. So what distribution should you expect? That system are not the physically allowed system. N tends to zero, V tends to infinity, or n other these two coordinates are not physically allowed. And
How to tackle
also, uh,
how
again,
to tackle this type of system, this
these
type of
system are not this type of system are not we can't obtain this type of system in a real world. That's why this limit appears. Na, this limit says that in which system this limit is maintained, only that system are allowed. That system can form, but this type of system can be formed because here the thermodynamic limit is not obeyed. Okay,
Okay, thank you.
only these two are allowed: the quantum thermodynamics and the classical thermodynamics. Okay. Next question. Fluctuation. Fluctuation should I discuss? Okay, leave it. We must discuss other questions. Entropy, you know. Second question. No. Okay. So let me discuss the question first. Okay, 1 minute. I have written down the question. Just let me find out. Okay, one question I forgot that in last class we discussed. Not I said that the entropy part I will discuss in next class. So here I should discuss the entropy part. What was the question that writing the question again? Consider a system of n number of non-interacting distinguishable particle where each particle can be in three energy levels. The lowest one called the ground state is non-degenerate and its energy is considered to be zero. The middle one at energy epsilon is doubly degenerate or twofold degenerate. Both are same. One twofold degenerate. The highest highest one at energy 2 epsilon is triply degenerate. Considering canonical ensemble, calculate the internal energy and entropy. Okay. So this question I did half portion in last class. In today's class it will be more clear because in last class I did not discuss that canonical part. So just wait. So means you have a uh, system which with n number of non-interacting distinguishable particles. So that is the macro state. In macro state there is a n number of particle, non-interacting particle, obviously. That n number of non. Here you can understand the relation between the capital Q and the small q. It will be clear. So n number of particles are there. So n is constant. Obviously, volume will be also constant, and canonical is said. So T is constant. So NVT is constant. Okay. Now you have to make infinite number of copies to create the canonical ensemble. Then you have to calculate the average. We will not do that. We will know the formula directly. All treatment has been done to achieve a formula, and we have to use that formula to consider the canonical ensemble results. Okay, so you have to calculate the E average. Okay, before that, you know the canonical ensemble partition function NVT is sum over j e to the power minus beta EJ NVT. Okay, one question you may ask that. Okay, let me clear that. Why GJ is not written here? Because you have seen in molecular partition function GJ was mentioned. Correct. So, but here we generally we don't write GJ. We always write this J. That means we are not considering the levels. These are states. Okay. So that's why. Okay. So that does not mean that all states are non-degenerate. States may be degenerate, but as we are considering the states, so that's why GJ will not appear. You know that when the GJ will appear, when you know that we are considering the level. GJ is the degeneracy of the level. That means the number of states under a level. But here we are considering the states, so no need to consider no consideration of the figures. So this is the Q. Okay. Now, current participation function, you have to calculate the internal energy. Okay, internal energy. What will be the internal energy? And what is said here that okay, lowest energy. Now the picture, that picture is okay, okay, it's very important. We said here that under this macro state, there are three energy levels: ground, first, second. Three energy levels are there. Ground one is zero. After that, this epsilon, it is 2 epsilon. It is doubly degenerate, it's triply degenerate. This is the molecular picture. This is not the ensemble picture. In ensemble picture, there is no energy level of the molecules. There are energy levels of that copies of the ensemble. That is different. Here we have not make any copies. So this distribution will give the molecular partition function. How? The molecular partition function Q, you know that is essentially Gj e to the power minus beta epsilon j. You see that capital E means the energy of a particular copy of that macro state. Okay, but this small ej is the energy levels of that molecular distribution. So two things you should be understand. confused. Okay, here we have infinite number of copies. For each copies, under each copies there are molecular distribution. That is epsilon j. That energy levels are considered by epsilon j, and the molecules are nj, which we have already discussed till last three classes. But in canonical ensemble, you have that you have a macrostate and you have the infinite number of copies of that macrostate, which are called microstates. That microstate also has different types of energy. There are energy levels as well. In these copies, under these copies also there will be energy levels, that there will be, that energies are called EJs. These are EJs. These are energy of that copies. Let's say there are AJ 10 microstates, 10 copies are there having energy E0. 15 microstates are there having energy E2 or E1. Like that. That AJ and EJ, AJ number of molecules, AJ number of copies are there with the energy EJ. That is the energy of a ensemble. And these two things are different, but these two things are related as well. That will, for that we need to establish a relation between capital Q, small q. Here the particles are, here the particles are non-interacting and distinguishable. That's why it is very easy to relate. If the particle are interacting or the particle are indistinguishable, then the pictures will be different. Okay, here, so q is known. So you have to calculate the q, both q. Let's say for canonical ensemble and for this q, then you can relate these things very easily. Let me do that. Okay, so using this, you know very well what will be the energy E average. That will be epsilon j pj, and it essentially means that epsilon j to the power minus beta ej divided by q. Okay, okay. So just first I just established the relation. Okay, then it will be more clear. Okay, or you can write the explicit form of q as well. That does not matter. For canonical ensemble, you know this is the average energy, which was kb t square. Just few minutes ago I discussed this. This is the average energy. Understand very clearly. This is the average energy for canonical ensemble. That means this is the average energy for each and every microstate. There are infinite number of copies of microstate. For each microstate, the energy are different, as we have discussed here. These energies are not same. All energy are different because energy are exchanged. But there is average energy. Average energy means the average. So that should not be varied. So average energy means this means the average energy of this macro state. This is the average energy of this macro state. And you know this molecular distribution. This average energy is the average energy of a molecule. Both are not same. But now you know, as the molecules are non-interacting, again I am repeating, non-interacting and the molecule are distinguishable. So you can easily write down that capital E, this is the energy of that macro state, average energy of that macro state should be n into average energy of that molecule, because n number of molecules are there. So this relation you can directly write for, because this is the molecules are non-interacting and obviously molecules are distinguishable. So this is n times. So now if you compare, so what you can write, this is kb t square dln q del t n v equals to capital N kb t square. You know this formula, dln q dt capital V. That's why you see here no n is there, because n is because this is for one molecule. So how n can be there? N means the number of molecules. So if you equate this, so easily you can see this will be dln q dt nv equals to n into dln q dtv. Okay, so from here, you if you want to calculate the relation between q and, so it's clear. So it should be this. Okay, because there is ln, so n will be goes here. So q should be, or more general, you should write q n v t equals to q to the power n. Here, this is canonical ensemble partition function. And this q is molecular partition function. Okay, so q to the power n will be there. So here we have to calculate the uh, e. This e we have to calculate. So there are two methods. Two methods. We have in last class we have calculated using this. So both method will follow. So we have to calculate. First, we have to calculate the average energy, internal energy U. That essentially means the E average. That essentially means this. So first, let's say we can calculate the method one. First method. Let first we calculate E average. So what will be E average? E average is GJ. Sorry, EJ PJ. So it is EJ epsilon j e to the power minus beta epsilon j divided by small q. Correct? So this is and q. What is q? Q is sum over gj e to the power minus beta ej. So you can write it for ground state, it will be 1, for it is 2 into e to the power minus beta epsilon plus 2 into e to the power minus 2 beta epsilon. Okay, so if you put it, so what we will have that it is for ground state E0 is 0, so it will be 0. For first excited state epsilon e to the power minus beta epsilon. For second excited state it is 2 epsilon into e to the power minus energy, what is energy, e to the power minus beta 2 beta epsilon divided by q is 1 plus beta epsilon plus. Okay, this is average. Is it clear? Okay, or you can write it. Okay, for okay, this is correct. Or now let me discuss another method. Okay, is this clear? Okay, ejpj you know, right? So what was that ejpj? It is ej e to the power minus beta ej divided by q. And from here you know what was the formula, that it is minus 1 by q dq. Better to use this formula. This was the formula for, the average energy for a molecule. This is the average energy for one molecule. And now q is already we have discussed similar way, gj e to the power minus beta ej. So it means 1 plus 2 e to the power beta epsilon plus 3 e to the power minus 2 beta epsilon. So del q del beta constant v, that will be 0 plus, not plus, minus 2 epsilon e to the power minus beta epsilon minus 6 into e to the power minus 2 beta epsilon. So the average energy for a molecule will be 1 by q minus, there are two minus and here is a minus, that will be gone away. So it will be 2 epsilon there, 2 epsilon e to the power minus beta. Already I had written 6 epsilon e to the power minus 2 beta epsilon. and q was 1 plus 2 e to the power minus beta epsilon plus 3 e to the power minus beta epsilon. So this is our E, average energy for a molecule. Okay, now we have to calculate the capital E. Capital E is just n times E. So we have to multiply each term with E. So it will be 2n E, not E, this is epsilon, 2n epsilon e to the power minus beta epsilon plus 6n epsilon e to the power minus 2 beta epsilon. So this is our internal energy. Now if you calculate the entropy, how you can calculate entropy? S average. S average you have to calculate. So how you can calculate S average? This is already discussed in class. The formula for S average, that is N kb ln q plus internal energy. Okay. So this part is known. Just N kb ln q you have to add. So it is N kb ln q is ln 1 plus 2 into the power minus beta epsilon plus 3 into the power minus 2 beta epsilon and plus the internal energy, which is already written over here. This is, so this is our entropy part. But this we have calculated using the molecular partition function. But same thing we can calculate by canonical ensemble partition function. That is asked in the question. We have to calculate by using canonical ensemble partition function. That we have to do here. So q we know. This q is known. This is 1 plus 2 in, we have to check whether the both definition matches or not. This is our partition function, molecular partition function. So what will be q? Canonical ensemble partition function. That we have mentioned that q to the power n. So it will be 1 plus 2 beta epsilon plus 3 into the minus 2 beta epsilon to the power n. Okay, this is capital Q. So again we know, so del E, E average is actually minus 1 by capital Q into del Q del beta under constant N and V. So we have to calculate this part. So del Q del beta at constant N and V means del beta of this part 1 plus 2 e to the power minus beta epsilon plus 3 into the power minus 2 beta epsilon to the power n. This part you have to calculate. Also where n and v is constant. So how you can do this? Because here to the power n is there. So let us consider this part. This is actually q, right? Capital small q. So you can write it. This is just q to the power n. Just q to the power n. You can write it instead of capital Q. You can write small q to the power n, n and v. So here you can write it del q to the power n divided by del q into dq del beta. Okay, so n is constant. So what will be this? N into q to the power n minus 1. Oh, wait. It's correct. Q to the power n minus 1. This part and del q del beta. Del q del beta already you have calculated. What is del q del beta? This. This is del q del beta. So just write it. So del q del beta is minus 2 epsilon e to the power minus beta epsilon minus 6 epsilon e to the power minus 2 beta epsilon. And it is n into q to the power n minus 1. Okay. So del Q del beta is there. Now here is cap. So now, so E average is 1 by Q minus 1 by Q. So minus sign will be there. So 1 by Q, and Q is again Q to the power n. And here n into Q to the power n minus 1 into 2 epsilon e to the power minus beta epsilon minus 6 epsilon e to the minus 2 beta epsilon. Okay, minus sign is absorbed here. There was a minus sign. So what does it mean? N divided by Q into this part. Okay, so small q already known to us. So that is n into, so let me write 2 n epsilon e to the power minus beta epsilon minus plus 6 n epsilon e to the power minus 2 beta epsilon divided by q is already known to us, 1 plus 2 e to the power minus beta epsilon plus 3 e to the power minus 2 beta epsilon. So just check, both are same. This expression already we have obtained. This is using the canonical partition function. So this is possible as per particular distinguishable and particular non-interacting. You can write down this formula and you can easily relate. Okay. So similarly, what will be the formula for entropy? This formula is, this formula is using our molecular partition function. Okay. So just okay, one thing I missed. Oh, this is not E. This is E by T, E by T, and N E by T. N E by T will be there. So T is missing. Okay. This is the formula. T I missed. So it is, this is the formula. So just now you can write it with KB ln Q to the power n plus, this already it is known to you. So you can write it average energy. This is not average energy. This is average molecular energy. And this is the average energy of the system, or internal energy. This is not internal energy. Okay. I am repeating it again. This is not internal energy. This is average energy of a molecule. When you multiply it with n and all molecules are non-interacting, then it gives the average energy of the system, which is internal energy. Or you have to use the canonical partition function to directly evaluate the average energy of the system. And this is capital Q. So it is KB ln Q plus daily by T. Okay. Okay. So this is for distinguishable and non-interacting, non-distinguishable particle. Because this formula is for now ensemble, right? So under ensemble, particle may be uh, interacting. This is for non-interacting. Here you can equate both formulas because particle are non-interacting. But when particle are interacting, you have to use this formula. This is valid there as well. But you can't derive that formula from the molecular partition function when particle are interacting. What I'm saying, it may be confusing. I'm saying that, let's say for internal energy, this formula kbt square dln q dt, this is using canonical ensemble. There is nothing with the molecule that may be interacting, non-interacting, both are correct. But this and this formula is for average energy of a particular molecule. Okay, this is for average energy of particular molecule. And if the molecules are interacting, non-interacting, then you can relate this formula very easily just using this formula. That is the case. But this formula is valid for always, but particles should be distinguishable. But here, this is for uh, in this non-interacting particle. Okay, so probably it's clear now. Okay, so let me stop here. If you have any question, you can ask. I think the partition function for canonical and molecular both are not same. This is clear, but that can be related, and there are several relation between those when changing the condition. You will see later that this q, capital Q to the power n, this is for this non-interacting distinguishable particle. If the particle are indistinguishable, then these will appear for bosonic. And I said in earlier classes that for fermionic, it is not straightforward. For fermionic, there is no relation, direct relation. Okay. Okay. So if you have any doubt, you can ask.
So I have got one question regarding assignment 4.
Assignment 2.
4, question
Okay.
number 2.
Okay. 1 minute. But assignment 4 deadline is not over. So,
That won't be
okay.
discussed. Huh?
Let me check the question. We can check that question. Material can be diabetic, process failure. Okay, okay. This is answered in class.
Okay.
What will be the answer? Magnetization property. To have the demagnetization property or magnetization property, there may be unpaired electron.
Yeah,
Okay.
I'm ready. Yeah.
So now in benzene, is there any unpaired electron?
Okay, okay. I get the answer.
Okay.
Fine, thank you.
Okay. So if anyone does not have any question now, I can stop sharing now. Okay. 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 So we'll meet again in next week. Okay, please go through the lectures in next week lectures. And if you have any doubt regarding assignment or the lecture videos or other doubt, you can ask in next class. Okay, in next class we'll meet again. Okay, so now
Thank you.
you can. Okay, thank you for in class. Okay, so now I can hang up the call. Okay.